Can AI do math? And I don't mean 2 plus 2, I mean pure mathematics. The paper we're going to look at today is called Formal Mathematics Statement Curriculum Learning and presents an automated system to prove mathematical theorems in a symbolic fashion. What's even more crazy is that this system was able to solve 2 problems of the International Mathematical Olympiad, which is a contest that real gifted high school students get to take part in. This system is way beyond previous systems that have attempted anything like this, because formal mathematics and automated mathematics that uses algorithms to prove things lags a lot behind the informal mathematics that you might know. A lot of previous techniques relied on proof searching, essentially brute forcing their way to a proof, guided by some heuristics, and this paper improves on that drastically. It uses language models to guide the proof search, and it uses a technique called expert iteration to build itself automatically a curriculum of harder and harder statements to prove. Now, the implications of this are cool for math, but it goes way beyond math. This is essentially symbolic reasoning. It's the model teaching itself to learn more and more, and that's exciting for many fields of AI. So here's how it goes. This video right here is a paper review, a comprehensive review of me going through the paper, explaining to you what is in the paper, what its main contributions are, what I think are the weaknesses and strengths of the paper, and much more. After this video, you should have a good understanding of what is in the paper, otherwise I haven't done my job. In the next video, released tomorrow, I'll be interviewing the first author of this paper, which is a huge privilege. Because if you watched this video, you'll see that I have many open questions. I'm a noob at formal mathematics, and I suppose many people are. And therefore, even though the paper is written really well, I had a lot of questions, I even had some criticisms, and all of that was answered when I spoke to the author. So if you watch tomorrow's video, you'll get an insight into the behind the scenes of this research, how it came about, what worked, what didn't, how problems were solved during the research process, and much more. The author I'm interviewing has actually seen my paper review and is directly able to answer to any questions that I raise there. Please let me know how you like these formats in the comments. If you do like the video, please leave a like, tell someone to subscribe, and I'll see you around. Bye. Hello there. Today we're looking at Formal Mathematics Statement Curriculum Learning by researchers of OpenAI, EPFL, and Cambridge. This paper presents or applies the technique of expert iteration to the domain of proving formal mathematics statements. This is not enough yet. They also bring language modeling into the picture. So you have a proof searcher in this paper, or a proof search procedure that is guided by language models to search for mathematics proofs, and then the expert iteration procedure makes the system better and better and better by always incorporating new statements that it has been able to prove into its training set. And so the domain or the difficulty of statements that it is able to prove expands iteration by iteration. The culmination of this is that they're able to solve 2 problems, I believe, of the IMO, of the International Mathematics Olympiad, which is a difficult math challenge for high school students. And this has implications beyond just math. So this can be applied anywhere where agents need to reason over some sort of symbolic structure. And, this is wide-ranging. This could be agents acting in the real world. This could be reinforcement learning things. This could be, assistance for clinical trials and whatnot. Essentially, anywhere where such a more formal system, more logical type of reasoning is required. So we're going to look into this paper and what they do. This builds on a bit of other work, but I think it can be looked at in isolation. So they claim right here in the introduction that deep learning has been very good at sort of many tasks like, language modeling, there's vision, image generation. However, they say it has not yet enjoyed a comparable success in tasks that require extensive planning and symbolic reasoning. And the domain of mathematics proofs is a good domain because it
has these challenges, but also you don't exactly rely on external data that much. Like you can prove things in mathematics kind of by yourself in the basement, or in this case, you can verify a proof pretty quickly. So the challenges in this domain are it has an extremely large search space and an infinite action space. When you prove a statement in mathematics, there are many things you could potentially do, like infinitely many things. It's not only about manipulating the symbols that are there. Often you need to introduce new symbols. For example, they say you could generate a witness, like there exists an X that fulfills some things where X was never a symbol before. So you have like infinite things at your disposal. Now the question is, how do you prove a statement? Maybe we'll just a little bit go into how these mathematics proving things work if you really do them formally. So in their types of system, they have some kind of statement to be proven. So I'm going to call that statement S. That is a formal statement that just is essentially is the formalization, the exact writing down of something like a theorem as you would find it in a textbook. But instead of using words and language, it uses like a defined syntax in a predefined system. So how to prove this system? In order to prove this system, what you need to do is you need to build up a tree. So you need to decompose this system in some way into multiple sub-statements. And the way you do this is, as you would do as a human, you'd have some sort of a proof, and then you say, okay, in order to prove that, I need the following three things to be true, right? So these would be the three things, like this is a substatement 1, a substatement 2, a substatement 3, and generally the derivation from from this to this, I believe that's called a tactic. So you can apply tactics to sort of reformulate things into its sub things. I'm speaking very informally right here because, as you might guess, I'm also a noob in this domain, and I hope the interview will tell us a little bit more about how these things work. But as far as I understand, you want to decompose these things into substatements, and then the substatements, again, you can decompose into stuff, and this is a context-free grammar, right? So this a substatement like this should be provable by itself independently of the other sub-statements. And you build this tree for as long as you want until the leaves right here are either the sort of the preconditions for the theorem. So a theorem could be, for any two rational numbers. So if the leaf right here says, this is a rational number, then we're done because that's a precondition for the theorem. Also, if it's like some sort of a lemma that I already know, or if it's like a fundamental, how do you call them, an axiom. If it's a fundamental axiom, I also stop. So I'm going to build up this proof tree until every single leaf is either something that I already know or something that I can assume to be true. And then I've proven the original statement because the tree represents the proof. Now, how to build the tree? That is the question, right? I could derive many different substatements from the top statement. The fact that I derive these particular ones that then lead me to a proof, that is the magic of proving things in mathematics, right? That's what mathematicians do for a job. And you can already see that this is not an easy thing. You might think of something like AlphaZero, AlphaGo, and that is a good guess. But whereas AlphaGo has defined actions, so all of these things that AlphaGo could do are pretty defined, like how it could expand the tree. Not in the case of mathematical proofs. There's a complex and infinite set of tactics, potentially involving exogenous mathematical terms that have to be generated. So quite a challenging domain. The other one, so there's the infinite action space, which is one of the problems. The other problem is this no direct self-play setup. So whereas in something like AlphaZero, I can train with self-play, in mathematics proving there is no adversary. I cannot have a two-player game and the two players get better and better and better. It's a statement, you can either prove it or not. Like that, it has the difficulty that it has. There's no opponent that can be hard or easy. However, so they say it prevents the naive application of the symmetric self-play objective. However, they say that they observe that the key role of self-play is to provide an unsupervised curriculum. And I'm not exactly sure, honestly, how they arrive at that statement, if that is just sort of their hypothesis right here, and the paper validates it. I don't see any exogenous reason why that might be true, but it is a reasonable statement to make, right? The self-play is really good because both opponents start very weak, and then they all get sort of better in steps. And that is essentially a curriculum. So the question is, how can we come up with an automated way to generate a curriculum for proving formal math statements? That is going to be one of the challenges. The other challenge, the challenge of infinite action space, they say that this has been addressed in past work by sampling from a language model. We're going to look a little bit into how this is done, but this is by the same authors. So they have previously dealt with this by having the proof search, like the thing that decides what node to expand in the proof tree, be guided by a language model that has been trained on a number of proofs and that sort of takes a good guess at what to do next. So it kind of guides the search, much like the value and policy networks in like AlphaZero guide the tree search, because that is also inherently too large. So they say they empirically show that when the difficulty of the auxiliary problems is varied, we skipped a part. So they say we propose to supply auxiliary set of problem statements without requiring proofs of varying difficulty. We show that when the difficulty of these auxiliary statements is varied enough, a simple expert iteration procedure is able to solve a curriculum of increasingly difficult problems. And so what they're saying is they're going to provide, so here is maybe, statement 1, statement 2, statement 3 that I want to prove ultimately, and these are really difficult. So what I'm going to do is I'm just going to put like statement 4, statement 5. I'm going to put these statements in here. I don't know what's wrong with the pen. Sorry. I'm just going to put these statements in there, and as long as they vary in difficulty, so there is like a difficulty gradient, and I just fill sort of the space with statement 6, statement 7, with various difficulty statements. What I can do is I can do an expert iteration procedure. So what does the expert iteration procedure do? Essentially, it just says that I start with some sort of a model that can solve some kind of a difficulty of statements. So let's say S6 and S7 are the easiest ones. Then I take the results of that system and the proofs it generated to retrain the same system. And that would result in a better system. And the better system now would be able to solve slightly more hard statements. And, since I now solve these slightly more hard statements, I can feed the proofs that I found back into the system, right? Train them on those proofs because I now know the proofs because I found them, and that system will get even better. So the expert iteration procedure is the act of always going to your best system, gathering the data that it has figured out through, guiding the search, then taking that data and retraining the system on this new data to make it even stronger. Right. This is based on two facts. You can't just do that with any system, right? This is based on the fact that here a machine learned system interacts with a search system, and the interaction is what makes the difference. So the combination of the two is better than just the search system, and better especially than just the machine learning system. So you can, if the machine learning system itself has a certain performance, adding the search on top will increase that performance and therefore allow you to get to more and better training data that you couldn't have just gotten with the ML system itself. If you just had the ML system, you just be stuck forever in a loop of always having the same difficulty, because all you do is feed the output of the ML system back into the ML system. But if you add a component on top that makes it stronger, that gives you better data, that can make the ML system itself stronger, then you add the search again, that will make it even stronger in combination. So that is the story of expert iteration and of this paper right here. They go a little bit into the environment. They have this lean environment, which I have no clue about, but this is like a formal environment for mathematics proofs. One of many, I'm being informed. There's also one that's called MetaMath, and apparently lean benefits from higher level tactics, which were shown to be beneficial in this context. But essentially for our purposes, it is, and also the proofs, lean proofs are typically 10 times shorter than other systems. But, for our purposes, just assume that we have some kind of a system where we can build proofs like this tree right here from statements. So they next go into expert. So they have a bit of data sets. That's what they describe here. We go into expert iteration. Expert iteration consists in iteratively training models on their previously sampled trajectories. That's essentially expert iteration. As for a model, they use decoder-only transformers. So they use language models, which just shows you sort of the versatility of language models. The biggest model, I think, that they use uses 36 layers and 700 million trainable parameters. So this is not too big of a model, right? This is a reasonably sized, it's big, but it's not like GPT-3 big. They pre-train this, which I found interesting, on a combination of mathematics data sets, but also Common Crawl, which is a language, it's a web scrape, right? That is very interesting that the pre-training happens on natural language and not just on mathematics data. Maybe you need this many tokens to pre-train the model, because the model itself is kind of big. But I'd wonder, what kind of difference that makes, and what the transfer is from the natural language to the mathematics, because math is very cryptic. Not even sure if they have. Let me find a proof here. Maybe they've listed. So yeah, you can see these are sort of the things you would find in, this is an internal trace of this lean environment, or their gym environment around the lean environments. So you'd have like these tactic states you can see right here. These have nothing to do with natural language, right? Then you have the tactics that you run. You apply this nat prime dvd mul hp.mp tactic. I have no idea what it is, and that transforms the above tactic state, I believe, into the bottom tactic state. I'm not going to parse this because I have no clue what it means, but you can see that these statements, they're very formal and they have nothing to do with natural language. Still, obviously, humans made them as a series of characters, and therefore there might also always be some transfer. So how do they train this? How do they train this thing? So the transformer is trained to suggest kind of what to do next in such a proof, and that is called a proof step. So the proof step objective that they train the transformer with consists in generating a proof step, which is a tactic, given a goal, which is a tactic state. So you're trying to get somewhere, which is the root of the current tree or subtree you're considering, and you're generating a tactic, which means like how to expand the tree, given that you are at this particular root. And they also condition this objective on the current declaration, which is the theorem name, which remains the same throughout the proof search. They give some explanation why they do this, but essentially what they train the transformer with looks like this. There is a keyword decl, then there's the declaration, which is the name of the theorem. Then there is a goal, and then here you put the goal state, the tactic state that you want to achieve, and then the keyword proof step, and then here is where the proof step goes. So during inference, obviously you leave this away and you let the language model generate this part, but during training you put right here any proof from any proof that was successful, you'd put the corresponding proof step there. So this is a language modeling objective. You just train on all of the proofs that that are true. You put them into this particular form. You put all of their individual tree expansion steps into this particular form, and you train a language model on it. And that apparently works pretty well. This is already from their previous work that this works pretty well. They explain this here. The rationale for conditioning on the declaration name is to hint our models on the position of the current declaration in the mathlib library. It can be considered a weak proxy signal for the large amount of information not shown to the model. So there is available imports, currently open declarations, module names, notations, declared instances. So, and that is where I really am a noob. There is this mathlib library, which is a library inside of this lean environment. And I'm going to guess the analogy would be like, it has a bunch of functions you can call. It has a bunch of stuff there that you could potentially use. And obviously this is not going to all fit into the little context that we have right here that we're going to feed into the transformer. So what you're going to do is you simply give this declaration name. And if the model has seen enough of those things, it obviously, some of these function calls will be in this proof step right here, if you start out with proofs that already exist. So some of these function calls will be in there, and the declaration hints sort of where in the library you are, which means that which functions you can currently call, which variables exist, and so on. I'm not exactly sure, but essentially I would read the declaration. If I were a programmer, I would read the declaration as maybe the project and the file I'm currently in and what imports there are. I would read the goal as the function definition, the function header, and the doc string that tells me what should happen in this function. And then the proof step, I would consider the function itself, the implementation. That is a very bad analogy, but approximately like this. It's a weird mix between programming and mathematics, this formal mathematics proofs. So they trained the language model on this. So now the language model can suggest new proof steps. You give it the declaration and the goal, it can suggest new proof steps, right? That is one thing they train the language model with. They, at the same time, train it also with this proof size objective. So they give other inputs to the language model that they train it on. Again, we have the declaration name, we have the goal, but then we have a different keyword instead of proof step. Now we have the keyword proof size, and then here is a proof size bucket token. And that's simply a letter from A to K, and that letter encodes one of 11 buckets. The buckets represent the size of the proofs. Again, during training, we know the proof size, right? Or the size of the proof step, or maybe the size of the whole proof. I'm not entirely sure. I think it's the size of the whole proof. Yeah, it represents a proof size estimate bucket for the current goal. Okay, so for the proof of the current goal, how long is it? And during training, we know it, so we just put it here. During inference time, again, this is the thing that we are going to let the model predict. So the model should guess how long a proof is going to be without necessarily producing it. That's what this keyword up here does. So the bottom one simply says, how long is it maybe, probably going to be? And this, it's pretty neat how they do it. So they have these 11 buckets. Infinite proof sizes go to bucket 0, and then bucket 1 gets the longest proofs, bucket 2 gets slightly smaller proofs, and the shortest proofs go into bucket 10. Why do they encode it like this? Now it comes to the place where how or what do you search? So you're now in the proof search, right? You're in inference mode. You ask your model to suggest a bunch of these proof steps to you that we saw right here. So you ask your model, please suggest a bunch of those proof steps. You sample from the model a bunch of times. And now which one should you do? Of course, you could go by, I guess, the log, the likelihood of these proof steps. But as far as I can understand, they weigh the tactics that they want to use. So they value different goals. This is about which goal do I want to pursue next? Okay, so they ask themselves, which goal should I produce or should I pursue next in my proof search? To value goals, as we run proof searches, we sample the proof size bucket token and record the logits for each viable bucket and use them to get a weighted average with the following formula. So the formula itself is not really important, but what is important, they use the prediction of how long a proof is going to be to guide their selection of goals, which means that the exact way they do it is they say if a model assigns P0 equals 1, which means that the model puts all the weight on bucket 0, which, if you remember, is the infinite proofs. So if the model predicts this proof size is going to be infinite, which means that it's not going to work, right? The proof size infinite means that it hasn't been proven yet, right? The proof search or the data set hasn't been able to prove this particular statement, so the size is infinite. Then the value, as you can see, is 0. So we don't want to go after something where the model is absolutely sure that the proof size is infinite. It's never going to be absolutely sure. But if that were the case, the value would be 0. Conversely, if a model is very sure or absolutely sure that this proof is going to be in the shortest bucket, then the value is 1. So this is a number between 0 and 1, depending on how short the proof is. So they say it prioritizes goals that potentially lead to shorter proofs during proof search. So that's how they guide their search. Excellent. So these are the two objectives they train with. The one objective is to make the model suggest the tactics to use, and the other one is to guide the proof search by training the model to predict how long a proof is going to be. So yeah, the next topic right here is how they bootstrap the models. So in this expert iteration, you always train on your own outputs. However, there needs to be like some sort of a starting point, right? Bootstrapping, they say, consists in the step required to train an initial model on both the proof step objective and the proof size objective. They have two initial models, in fact. They have a data set which consists of some of these proofs that have already been proven, and they train a model with just the proof step objective, which is called theta 0. So that's the initial model. Then they use the initial model to sample proofs for the statements in this mathematics library. So they already use the model to generate proofs. We denote the set of successful proof searches created in process as S0. Using S0, we create a data set. So the expert iteration process essentially already starts. So they're going to concatenate the original data set, the original data set, and a deduplicated set of proof steps extracted from the proofs in S0, and a deduplicated set of proof size tuples extracted from the proof searches in S0. So now they're going to use whatever they output as proofs in the last iteration. They're going to take that into the data set. They're going to create these proof step sentences. I'm just going to call them sentences because we're language modeling right here. They're going to create these proof step sentences like this one. They're going to create these proof size sentences like this one. And then they're going to train a model again on that. So they're going to take the theta 0 and they're going to train it on that new data set. So that gives them theta 1, which is trained on both the proof step and the proof size objective. And theta 1 is our first model in our expert iteration. So now we are simply going to repeat those things. Each iteration K consists in sampling proof searches for statements using the current model, filtering successful proof searches to extract a new data set, and fine-tuning the theta 0 on it to obtain theta k plus 1. Note that they don't go from theta 0 to theta 1 to theta 2 and so on. They always go from theta 0 to theta 2. Then they use theta 2 to generate a data set. Then they fine-tune theta 0 again to get to theta 3. It'd be interesting to know why they do it this way. Maybe if you continue fine-tuning, you're already sort of locked into something. So the knowledge comes, the unified knowledge comes from, you can see this right here, the fact that the data sets they generate comes from the unified set of all the statements they've proven so far. So all the proofs they found so far, they all go together into one big data set for the next step. So technically every model can like relearn the proofs that the last model also knew because they're in the same data set. And potentially they also say that they deduplicate proofs, which means that for the same statements there could be multiple proofs and they will always take the shortest one. So that might be even a disadvantage if you were to tune from like theta 2, which would still have learned a longer proof for a particular statement, and you'd have to like forget that. It's probably just easier to scratch everything and start with the shorter proof in your data set. And yeah, that is it. That's the expert iteration process. They get a new model, they use it to generate new proofs, they add the proofs to the set of things they know, and there is a set of things they don't know, right? Because there can also be bad proofs which serve as negative examples, which is also good. Right? We can handle negative examples, and then they get better and better. So now they are going to evaluate this right now. You see that they have various ways of using this model. There's pass at 8, there's pass at 1, which essentially means like how many tries they give per expansion step. Like do we try once? Do we try 8 times? Obviously, the more you try, the longer your searches run, but also the higher your chance of actually finding something useful. And these things are mostly proportional to each other. So it's just a matter of computational effort. You can see that with expert iterations, so the x-axis right here is number of expert iterations. You can see they do 9 expert iterations. On these data sets, in general, you see an upwards trend. So more and more statements are able to be proven by the expert iterated system. And they have multiple data sets. This mini F2F is their final goal. This is made up of these various competition level statements, while the mathlib, that is more of these kind of formal proofs from these formal environments. And they do see that the overlap isn't too great right here, and you can see that here as well. The scaling only kind of sort of kicks in after a while. What also astounded me is that in both cases you have solve rates actually go down intermittently, and I would be very interested, why that is. That could be just like an effect of size or something like this, but like, why do solve rates go slightly down, or is it just noise? I have no idea. You also see these are the cumulative pass rates, and so this is the expert iteration model, and this is the sample only model. So in the blue model, you run expert iteration, which means that you sample data and then you retrain, and then you sample again, and then you retrain. And in the orange model, you only sample. So you only use, I believe, the theta 0, which is the initial model. You use that to guide your search, but you never retrain on the things that you found. And interestingly, obviously, I guess, the expert iteration model way outperforms the sample-only model. However, the sample-only model uses less compute because it doesn't have to do the retraining. So once you adjust for that, you can see it's this line right here, where at first the sample-only model is better, because the expert iteration actually wastes time in training. But as you go on, if you give it more and more compute, the number of more statements that the sampling only model solves, it underwhelms with respect to what the expert iteration solves. And even on this data set right here, on this more distant data set, there seems to be almost like a little bit of a diminishing return in the sample only method, and after a number of expert iterations, the expert iteration method outshines the sample only method. We don't have an adjusted compute curve right here, but you can guess maybe that it might look something like this. Possibly. Just kind of like a constant over the originally orange curve. Orange curve bad. Yeah. Also, let me know how you like this pre-annotation right here that I've been doing now for 2 papers, I think. So I like pre-highlight them. I wonder how that's received, if that makes it more or less confusing. It just tells me a bit more where to jump to. So we get some results right here. The number of statements proved in mathlib train goes from 17,390 at iteration 1 to 19,476 at iteration 9, while the average proof length of these statements goes from 4.8 to 4.0. Right? We hypothesize that this continuously improving performance through expert iteration stems from 2 effects. So 1, the model finding new original proofs for the same statements, which would then be shorter than the original proofs, and 2, the model closing marginally harder statements at each iteration, which in turn provides more useful training data for the next iteration. By iteration 9, the model is trained on more than 90% generated data. So the original data set is like a small minority of the data that the model is trained on. Again, another property that I haven't even mentioned yet is that in proof search, you can verify a proof. Like, you know if a proof is correct, which in most domains isn't the case, right? So retraining on your own output is dangerous because you don't exactly know how good it is. But here you can just verify that it's good, and then you know it's good data, right? So it's a bit of a special environment, but I think we can still learn things from it. So what do? They first train this thing. So now I think the setup is clear, right? The expert iteration setup. And they also have made it clear that, we can reach harder and harder statements, but what we maybe can't do is just jump to hard statements. We need a curriculum, we need several various difficulties of statements so that we can sort of expand our knowledge again and again and again. And they first do that with synthetic data. So apparently what you can do is you can make a synthetic inequality statement generator, which gives you symbolic mathematical inequalities, and you can kind of control how difficult they are. So what they do is they just compose known inequality theorems, like Hölder inequality or something like this. They just compose them, and how many times they compose them, that kind of measures how difficult they are. So they have two parameters right here that control how difficult they are, and they generate 100 statements of low difficulty, like these numbers pretty low, and they formalize a proof for each. So this is kind of their seed set. So two things you need. So you need this seed set of proofs. This is usually like some sort of a data set. In their case, they combine this tactic data set that is their seed data set. They combine this one with these 100 statements that they generate, and they prove themselves, either themselves or automatically. So this would be the seed data set, and this thing right here, that's the curriculum, or just a collection of statements of various difficulties. The curriculum doesn't need a proof, right? This is the key part right here. The curriculum simply gives the model an opportunity to solve continuously harder and harder problems, going from the seed, right? So going from the seed, you only need to be able to solve the most easy problems in the curriculum, and then you can sort of rely on the expert iteration, on the self-bootstrapping to become better. Results are here. You can see that for a given, this right here it's one of the n numbers, this right here. So the color measures the difficulty. 0 is the easiest, 6 is the most hardest difficulty. You can see that even for easy problems, expert iteration just manages to solve much more problems. And for the hardest problems, the sample-only method, so if you just do proof searching without expert iteration, it doesn't solve any of the harder problems. Whereas the expert iteration, actually, if you see like there's like a tiny uptick at the bottom right here, it actually manages to solve some even of the hardest category. So that gives a bit of credence. They say here that the ND equals 6 remains completely out of reach of simply scaling the number of attempts per statements, which kind of means that you'd have to like invest a lot of compute if you just do proof searching to match how good expert iteration is. But compute by compute expert iteration is better. So they say, well, we're going to target this mini F2F data set, right? This is our final challenge. They say we curated and manually formalized a set of math exercises to target this data set. So this is going to be their seeds and curricula here. We hypothesized that if the difficulty of this set of statements was made varied enough, expert iteration could potentially leverage it to effectively shift our model's distribution closer to mini F2Fs and in turn improve their eventual performance on it. So they're going to build this curriculum right here. They're going to collect some like 300 statements. We manually formalized. It means just they bring it into the syntax. It doesn't mean they also prove these statements, right? So these will be these curriculum statements. These come from like books, math books that are used to prepare for math exams, which are much closer to this data set that they target. So this set of statements, this is this curriculum that I'm talking about, is the union of the statements in MATLAB train. They interestingly, they add these inequalities that they've generated to the set of statements, and also these manually collected things that they mentioned above. And with that, interestingly, they do in fact get a lot. They get better on this mini F2F validation set. So yeah, you can see that things go up, which is a good sign. Again, that you have like different parameters. This A parameter is also, I think, a parameter of how many times you sample per expansion or something like this. I don't know. There are many, many parameters in these searches, but in general, just from what I've seen from this paper, is you can always trade off more compute, like trying more times, expanding more times, suggesting more steps to do. You can always trade that for a bit more performance, but the general direction, it doesn't matter in the general direction. That's that. Obviously, they are better than, like, the results are as you would expect, I think. So their models are generally better than, let's say, the other models that haven't been targeted at this data set, or the models that just do proof search. So they have a short discussion of model size. They say we briefly experimented with different model sizes and found that model size scaling is not as straightforward in the case of unsupervised learning. They found that bigger models are better in the sense that they consistently exhibit higher pass rate if you just sample once. However, despite that, it is often the case that for a fixed amount of compute, sampling more attempts from a smaller model leads to better final performance. So these are the sort of considerations that you have to do if you have two independent variables, right? You can trade them off against one another. Just for the scale, with their big model, running a full expert iteration, that's kind of one of these full expert iteration. Full expert iteration, do they mean all the 9 steps or just one step in the expert? I'm going to guess all the 9 steps. So the whole experiment to get to their model after 9 expert iteration steps required 2,000 A100 days to compute. That is insane. Running one full proof search, when properly parallelized, requires on average about 0.1 A100 hours of compute. So it's like still a minute of an A100. Crazy. Still, so the sizes here are enormous, right? And still they are able to solve 2 of these olympiad problems, right? With manual targetings, with manual data collection that is specifically targeted at that data set, and with 2,000 A100 days. And, they don't solve all of them, they solve 2. So I believe this field is still in its infancy. I believe there's lots of stuff to do right here. There's probably approaches that make these things a lot better. But I'm excited just because I think that is an area where deep learning, as they say, hasn't really pushed through quite yet. And I think there's a lot to do to bring down the requirements here and the methodologies that they use. I like the way they combine the language modeling with the proof searching. The expert iteration might also be a nice lesson for other fields. Like, how can we combine the neural models with some sort of search procedures maybe, or other heuristics to generate ever better training data that we can then feed back to the models. All of this is highly interesting, and let me know what you think, and bye bye.